Hi again, 254 friends. Here is part 2 of 4.2. We're going to now discuss the mean value theorem. The mean value theorem is a bigger version of Rolle's theorem. Rolle's theorem is a specific case of the mean value theorem. We'll talk about that in a minute, but let's look at our hypotheses and our conclusion of the mean value theorem. The mean value theorem has the same first two hypotheses of Rolle's theorem. We have to start with a function that's continuous on a closed interval and differentiable on the corresponding open interval. So these are my hypotheses. So they're the same as the first two of Rolle's theorem. The third hypothesis is eliminated in the mean value theorem, but we have a different conclusion. The conclusion of the mean value theorem is if these first two conditions hold, then we can find a point C in the interval where the derivative at C is not 0 any longer, but it's the slope of the line connecting the endpoints, f of b minus f of a over b minus a. So what does this mean? Well, back in the last part of 4.1, the first part of 4.1, we had to make sure that the output at the endpoints was the same. The mean value theorem eliminates that requirement, but thus has a different conclusion. So the output at B does not have to be the same as the output at A. So f of B and f of A do not have to have the same output. If they do have the same output, the mean value theorem still applies, but we're actually in a specific case, which is the conclusion of Rolle's theorem. So now what it says is that we have a function, it's continuous on this closed interval and differentiable. So we want to make sure we draw a function that passes through both of these points, is continuous and differentiable. So there's no holes, breaks, or jumps, no peaks, points, or places where the tangent is vertical. Now previously, the output at the endpoints was the same. We knew that somewhere the derivative between those 2 points had to be 0. This is a little bit different. This time we're looking at the slope of the line connected in the endpoint. So if we look at the line that connects the endpoints, let's see if I can do this and make it through. I did it, yes, right there. The slope of this line is just f of the change in y, f of b, minus f of a, all over the change in x, b minus a, and what mean value theorem says is now somewhere between a and b, there must be a point on the curve whose derivative is the same as the slope of the line connecting the endpoints. So if imagine you're walking on this line, where would you be standing and have the same exact steepness here? So you can kind of like gauge it with your pen. That would be the steepness. That would be the steepness, you know, here, it looks like about, in my picture, it looks like about right here, the steepness would be about the same as the line connecting the endpoints. But notice there's also a point down here. So the mean value theorem isn't restricted to just one value. In this particular case, I would have two values of C. So we'd call this C, I'm going to call it C1 for my first C, and C2. So what's going on here? So this would be, and the slope here would be the derivative at C2, and the slope here would be the derivative at C1, and it would be the same as the slope of the line connecting the endpoints. Now remember, the slope of the line connecting the endpoints is the average rate of change of the function over that interval. The slope at a particular point is the instantaneous rate of change. So this is telling me that somewhere in the interval, the instantaneous rate of change has to be equivalent to the average rate of change. The example I use regularly in class is when I take my trips to Rochester to visit family and friends out there, it takes me 6 hours. So my average speed is 360 miles, because that's the distance from Norwich to Rochester, divided by 6, so I average 60 miles an hour. But at every instant in time, I'm not traveling 60 miles an hour, but at some point in time, I had to be traveling 60 miles an hour. So the mean value theorem says that your average rate of change has to equal the instantaneous rate of change at some point in the interval. So let's look at an application of this. Let's apply the mean value theorem to the function f of x equals x to the 2/3 on the interval from 0 to 1. So first thing we have to do, are hypotheses satisfied? So f of x equals x to the 2/3. It's a cube root function with with an x squared underneath. Cube roots are continuous and differentiable everywhere, so we have no problem with this function. All right, so now here's where it's a little bit different. Last time we had to check with Rolle's theorem that the outputs at the endpoint was the same. Here, they don't necessarily have to be the same. But what I like to do is I like to make a table of values, and I just put the end points of my interval as my input. I'm going to stick them into the function. So if I stick 0 into the function, x to the 2/3, the output is 0. I stick 1 into the function, 1 to the 2/3 is 1. And then I calculate the slope of the line connecting these points. So this would be A, this would be B, this would be f of A, and this would be f of B. So the slope is the change in y over the change in x. So the slope of the line connecting the endpoints is 1. Now, the next step, the mean value theorem says, we can find some point in the interval between 0 and 1 where the derivative at that point is equal to the slope that we just calculated. So I take my function, I take its derivative, oops, 2/3 x to the negative 1/3, and then the mean value theorem says that we're going to be able to find a value of x such that 2/3 x to the negative 1/3 equals the slope, and we get this point from the slope of the line connecting the endpoints. So now we just have to solve this algebraic equation. All right, now here's where is a test of your algebra skills. 2/3 x to the negative 1/3 equals 1. Well, I'm going to multiply both sides by 3/2. Get rid of the fraction on the left side because we want to isolate the variable. So we get x to the negative 1/3 equals 3/2. All right, well now here's a little bit, this gets a little bit tricky. So we have to strategically raise both sides to a power to get the x by itself. Well, I want to pick a power such that when I multiply it by 1/3, my powers will disappear or become 1. Really not disappear, we want it to become 1. So the key here is to multiply both sides. I'm sorry, not multiply, raise both sides to the power -3. So x to the negative 1/3 to the negative 3, powers to powers we multiply. That's just going to become x to the 1 is equal to, well, 3/2 to the negative 3 is just 2/3 cubed. If you have a fraction raised to a negative power, you can just flip the fraction and change the power to positive. So x is equal to 2 cubed over 3 cubed, or 8 over 27. So 8 over 27 is the value of this function on the interval 0 to 1, where the derivative equals 1. Let's see if we can take a quick minute and look at this graphically. So I'm going to graph this function, x to the 2/3. Now be really careful when you are graphing your radical functions. You want to make sure that the fractional power is completely in the numerator. Depending on how old your calculator is, you may need to put parentheses around the power. So I'm going to graph this guy. We're going from 0 to 1. Oops. And yeah, it's tough to really see what's going on there. So I'm going to do my window. I'm going to change it from 0 to 1 because that's all I really care about. And my y values only range from 0 to 1 anyway. So I'm going to go from 0 to 1.5. Let's see if I can look. So this is what this function looks like. Kind of just looks like a little arched curve. So for simplicity, I'm going to just draw this. Okay, at 0, we're at 0. At 1, we're at 1. It kind of behaves like this. So this is f of x equals x to the 2/3. If you look at the slope of the line connecting the endpoints, the slope of this line is 1. And 8/27, it's about, I don't know, about like right here. About right here, this is the slope of the curve right here at 8/27. also equals 1. So the average rate of change from 0 to 1 is 1. The instantaneous rate of change at 8/27 is also 1. All right, try one more example. Let's see what I got for you. This one's a little bit trickier. Apply. Oops, you know what? I already wrote it down. So we're going to save myself the hassle of rewriting it. Let's apply the mean value theorem to the function f of x equals x over x plus 1 on the interval, -1/2 to 2. So rational functions are continuous on their domain and differentiable on their domain. We learned about that back in chapter 2 and 3. So the hypotheses are satisfied. So what we need to do is create our table of values and find the slope of the line connecting the endpoints. Okay, so not as super obvious, and I'm going to actually take my calculator to help me do this work. I'm going to throw this into my calculator. I'm going to clear this, and I'm going to do x divided by x plus 1. And I'm going to graph that guy. It's not the window I want, but that's okay. I'm going to do my window. I'm going to go, whoops, clear. I'm going to do zoom. I'm going to go zoom standard, go back to my standard rectangle. So funky things are happening. This function's not defined at -1. So the only place we have a problem here is -1, but that's not part of our interval. So we're only looking from -1/2 to 2. So we are good. I'm going to go second calc, and I'm going to do the value at -0.5. See if it gives me a nice number. Oh, it's just -1. And then I'm going to do the value at 2. And the value looks like it's 2/3. So what I'm going to do now is find the slope of the line connecting this. 2/3 minus -1 all over 2 minus -1/2. And I'm going to recruit the use of my calculator to find this to save us some time. So I'm going to do parentheses 2 divided by 3 plus 1 divided by 2 plus 0.5. Let's see what we get. Math, enter, enter. So the slope of the line connecting the endpoints is 2/3. So if I go back into my graph and I look from -1/2 all the way out here to 2 and I connect that, the slope of the line connecting the endpoints is going to be 2/3. So now what we have to do is take the derivative and set it equal to 2/3. So this is a little bit trickier. Good practice with our differentiation. So the derivative is, well, the derivative of a quotient. We have to use the quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. And then we set the derivative. The mean value theorem says take that derivative and set it equal to the slope of the line connecting the endpoints. I'm going to take that derivative. I'm going to simplify as we go along. X plus 1 minus x. It's just 1 over x plus 1 squared. So the mean value theorem says take that derivative. If I distribute, I get x plus 1 minus x. It's just 1 in the numerator, and that equals 2/3. I'm going to cross multiply, and I get 3. It's equal to 2x plus 1 squared. This is a quadratic equation. I'm going to distribute the x plus 1 squared, subtract the 3, and solve it. So it's going to be 2x squared. The middle terms will be 2x, so plus 4x. And then it would be plus 2 minus 3. So 0 equals 2x squared plus 4x minus 1. All right, well, we can try factoring, but I'm going to save you the hassle and let you know that this is not a factorable quadratic equation. So we're going to have to use the quadratic formula. -b plus or minus b squared minus 4 times 2 times -1 all over 2 times 2. That's going to get me -4 plus or minus the square root of 16 minus 4 times that. It's going to be 24. all over 4. We're going to use our properties of algebra. -4 plus or minus, -4 over 4 plus or minus the square root of 24 is 2 square root of 6 all over 4. So our two values are -1 minus the square root of 6 over 2 and -1 plus the square root of 6 over 2. Now remember, our interval, we're only concerned about from -1/2 to 2. And if we pop these numbers in our calculator, you'll see that, well, let's see. -1, I'm going to do -1 minus the square root of 6 divided by 2. And does that fall? Whoops, nope, don't do that. Sorry, it's not my calculator. I'm not used to this one. All right, so that's -2.2. So this does not fall within our interval, but I'm going to do it again. I'm going to change my minus to plus. And 0.22, this one works. So therefore, the value of C in the mean value theorem that satisfies the conclusion of the mean value theorem is -1 plus or minus, nope, sorry, just plus the square root of 6 over 2. All right, that being said, your assignment for 4.2 to do. Read 4.2. You still should be keeping up with your exercises in the text. (1 to 17 odd), 21, 25, and 27. And your X, Y, Z homework. I forgot the equivalent for 4.2, but I did send you that spreadsheet with that information, so you are welcome to look that up. All right, see you in section 4.3.